Okay, folks, well, I can see we just hit or about to hit 1 minute after the hour. My name is Matt Thomas, and thank you for joining the USGS Landslide Hazards Seminar. This meeting is hosted by the Landslide Hazards Program and is co-organized with contributions from Stephen Slaughter and Jamie Kostelnik. For those of you that are new to this meeting, you have the ability to submit questions via the chat window or to use the raise your hand feature in combination with your microphone and video camera. We'll wait to the end of the presentation to take questions. So in the meantime, please just do your best to make sure your microphone is muted and your video camera is off when you're not intending to speak. Today is our 5th installment of a mini-series where we hear from our state surveys. These talks will provide an overview of state landslide expertise, focus areas, product types, as well as introduce the kind of most pressing landslide problems that the state faces. If you'd like to have your state landslide work spotlighted, please shoot me or one of the other organizers a message and we'd be happy to coordinate a date. Today we're joined by Lindsay Spigel, and Lindsay is originally from Ohio. She tells me this is quote unquote from away, as they say in Maine, and she received her MS and PhD in geography from the University of Wisconsin-Madison, where her research focused on quaternary geomorphology and paleohydrology. She's been working with the Maine Geological Survey since 2016, where she conducts surficial geologic mapping through the state map program, landslide hazards research, and education outreach. Lindsay, thank you so much for joining us today. I'll go ahead and turn it over to you.
Thanks for having me. Just gonna turn off my video here to save some bandwidth, and we can go ahead and get started. All right. Hi, everyone. Again, my name is Lindsay Spigel. I am a geomorphologist at the Maine Geological Survey, where I conduct surficial geology mapping and landslide research. Today, I'm going to give an overview of landslides in Maine from sea to summit, which are, in my opinion, a much overlooked hazard in the state. Of course, many might call me biased, because it's my job, but I usually only need a few LiDAR images to convey Maine's impressive landslide history. First, I would like to take this opportunity to briefly introduce the Maine survey to any of you that might not be familiar with our state and our program. The Maine Geological Survey is part of Maine state government, specifically the Department of Agriculture, Conservation, and Forestry. It has several bureaus, which are all pretty self-explanatory. The survey is a service program within the Bureau of Resource Information and Land Use Planning. We are a small group. Some of you may know Bob Marviny, our state geologist for many, many years, who just retired in 2021. Our geologist is Steve Dixon, who has also been with the survey for over 30 years and is a marine geologist. Pete Slavinsky is our other marine geologist, and I'll be sharing some of his coastal research later. Barry Berry and Amber Whitaker are bedrock geologists, and Amber is also a GIS guru who corrals our contract bedrock mappers. Chris Halstead is our GIS director, and basically nothing would work without him. Brian Gordon is a hydrogeologist, along with Dan Locke, who is not in the photo. I conduct surficial mapping through the state map program and associated GIS work, along with landslide research, and we all share educational outreach and miscellaneous duties. We have several bedrock mapping contractors through state map, and occasionally a couple of lucky interns. So hopefully that provides some context for our program. Despite our small numbers, we get a lot done. All right. So mass wasting in Maine can be roughly divided based on location and related surficial materials. So I would like to give a quick surficial geology overview using our simplified state surficial map. Due to isostatic depression of the land surface during the last major glacial advance, much of southern Maine was inundated by the late glacial sea as the ice sheet retreated to the northwest. Marine deposits accumulated in these areas and were subsequently lifted above sea level by rebound, as depicted in these cartoon illustrations here on the right. The approximate elevation limit of marine inundation, or the marine limit, is indicated by the dark blue line here on the state map. Glaciomarine deposits may occur south of this line, especially in lowland areas and closer to the coast. So most of the map is teal, which is no surprise, glacial till, but I want to draw your attention to the lighter pink units, which are fine-grained glaciomarine deposits that are highly linked to landslides below the marine limit. These fine-grained glaciomarine deposits are known as the Presumpscot Formation, named for exposures in the Presumpscot River Valley in southern Maine, which I will mention frequently throughout this presentation. It is a geotechnically sensitive deposit, mostly comprised of glacial flour silt that flocculated and settled out on the late glacial seafloor. It can liquefy and flow when disturbed or left unsupported, leading to landslides. Deposits can be massive or laminated and vary vertically and horizontally with very limited public studies of its characteristics, which is problematic. Near the surface, whether into a hard tan crust, as shown in the right photo here, which can be very misleading as unweathered portions at depth are typically blue-gray and stiff to very soft, as in this left photo here. Presumpscot Formation is functionally similar to glaciomarine muds found in eastern Canada and Scandinavia that also lead to landslides. More examples here. The left photo shows Presumpscot Formation removal from a major construction site in Portland where it is curling up like frosting. I also have a short video of me handling a core sample to show how soft the unweathered material can be. So hopefully this works. Very short. That again. Oh, no. Oh well. We can watch it again later if you'd like. All right, so with that quick and muddy introduction to Maine's surficial geology and the Presumpscot Formation, we can move on to their influence on landslides. As I mentioned earlier, landslides in Maine can be roughly divided into three groups based on location, related surficial geology, and landscape characteristics. But after a brief overview here, I will dive into each region with more specific examples, current research, and our public resources. Coastal landslides occur directly on the coast, and failures are usually related to wet conditions and coastal processes such as wave action and storm surges. They can involve a variety of materials, but usually occur in Presumpscot Formation, and they tend to be smaller rotational slides around a hectare or so. Inland lowland landslides occur away from the coast but below the marine limit. They can occur in a variety of materials but are usually related to wet conditions and Presumpscot Formation failure in river corridors and range from small rotational slides to very large spreads and flows. Inland upland landslides occur above the marine limit, usually in steeper terrain due to wet conditions with a variety of failure types and materials. Starting off with coastal landslides, coastal erosion and landslides get the most attention by far due to greater population density and very high property values. People think of Maine's coast as rocky and rugged with picturesque lighthouses everywhere, and we do have that. But there are also a lot of coastal bluff areas comprised of unconsolidated glacial deposits that are subject to erosion and failure due to regular coastal processes. And of course, sea level rise and increased storm severity may increase future coastal landslide activity. Maine coastal bluffs go through a natural cycle in which the base is undercut by wave action, as shown here in the cartoon diagram and this photo here on the right, eventually leading to slumping and sliding. But the failed material then acts as a natural buffer, protecting the bluff area until it is eroded and the cycle begins again. In this example from Brunswick, we can see fringe marshes out here formed by landslide toe remnants that clearly indicate this area is susceptible to failure. So geologists were not too surprised by this 2016 event. So the same house is circled in red in each photo for comparison. And I just want to note that the general location of each site that I show today will be marked with a red star on a Maine locator map so that you can have an idea of where this site is. The April 16th, 1996 Rockland Harbor landslide is probably the most well-known coastal landslide, if not the most well-known modern event in the state. It was a very typical spring event in which wet conditions led to a retrogressive rotational failure of a bluff section comprised of Presumpscot Formation. Liquefied Presumpscot Formation clearly makes up most of the tow, and the total disturbed area was about 3.5 acres or 1.4 hectares. And you can see some of the rotational component here from this tree that's tossed backwards. Thankfully, no one was injured, but 2 homes were lost. More photos here near the head scarp on the left, and this photo is a view from down here. You can kind of see how they match up. The brown material is weathered Presumpscot Formation and probably a little bit of sand. And on the bottom right, we can see blue-gray unweathered Presumpscot Formation in the crater, looking back up towards the house remains that are in the middle photo. It's interesting how the trees, 2 trees in this photo, stayed nearly vertical while they went for a ride, but this is not uncommon in these types of slides with sensitive clay. We have Rockland purchased and remediated the site, adding drainage, lightweight fill, and riprap. This is what it looks like today, looking up back towards the scarp. Was reworked within only a few years, and so now if you go down to the water, the riprap is exposed along with some of the remolded Presumpscot Formation. So this was not the first landslide in Rockland Harbor and probably will not be the last. Another major event happened in 1973, which is right here, but that had faded from memory by the 1990s. A view of the scarp is here in the left photo. So this scarp portion and many of the bluff sections have been engineered to hopefully reduce risk. And these are the noticeably smoothed areas on the Lidar image. And this is the 1996 area, which clearly looks engineered now. So whether this is a good approach is certainly debated, and so that's a nice segue into current bluff management approaches and research. As I mentioned earlier, my coworker Pete Slavinsky is a marine geologist who works on several coastal issues, including bluff erosion and management. Pete's recent research involves trialing different types of living shorelines, which involve modifications of bluffs or shoreline areas to reduce erosion and increase stability using local and mostly natural materials. In this example from Brunswick, an installation of logs and mesh bags filled with shells are meant to protect a fringe marsh area from erosion, which in turn protects the bluff areas here in the background. So far, this approach seems to be working fairly well at this location. Pete just went to visit it in January, and it's still there, which is good. This sandy eroding bluff on Lanes Island was selected for another project in which the bluff was graded to a more stable angle, and trees from the site were used to form a set of terraces that were planted with appropriate native species for stabilization. Unfortunately, this project has not held up very well for several reasons, but is clearly most compromised at the edges. There was only enough funding for a 50-foot long installation, and this certainly shows that bluffs can't be managed in piecemeal sections, which brings us to the challenges of coastal bluff management in Maine. So there are many obstacles to bluff management in Maine. High property values tend to discourage landowners from reporting issues or seeking help from public resources for fear of regulatory action or decreasing their property value. And many current regulations have loopholes or poor language that can discourage sustainable management options. The current coastal permitting process does not encourage landowners to collectively manage an entire bluff section, which can have a cascade effect. One person ripraps, altering the sediment dynamics, so then their neighbor has to riprap, and so on. Engineering is certainly a quick fix, while living shoreline approaches are dynamic and require maintenance, as shown in the right photo here. Plus, the local engineering community simply needs more education about living shoreline options. Many just aren't aware of this approach. MGS has many public coastal erosion and landslide resources all available for free on our website. The most items include coastal bluff maps, which are probably our only product used for regulatory purposes, in this case to determine building setbacks based on bluff stability. They were originally published in the early 2000s and are pretty frequently revised as we get better data or bluffs are modified. This is a screenshot from our web map where the public can easily browse most of our products. You can see the Lanes Island site here that I showed earlier is marked in red as highly unstable, and rightly so. We updated the Maine Coastal Property Owner's Guide, which is a fantastic detailed resource. There's also a multi-agency update on the state of Maine beaches put out every other year. And in a related theme, Pete and our GIS director, Chris, also recently put together a sea level rise ticker and dashboard for Maine's coast, which shows that many recent tide gauge measurements are breaking records, and not in a good way. Okay, so moving on to inland lowland landslides. This is my area of expertise and where I think that things get really interesting. Landslides have been a known hazard in southern Maine for hundreds of years, if not longer. As I mentioned earlier, most landslides in southern Maine are related to Presumpscot Formation failure in river corridors, usually due to wet spring conditions. Several events were documented in southern Maine during historic times, including these two landslides along the Presumpscot River in Westbrook. The 1868 event is the largest documented landslide in Maine at about 40 acres or 16 hectares. The right photo shows a view looking up into the crater, so the river is behind the photographer in this case. The flow morphology is likely the result of more sensitive Presumpscot formation in this area. The debris from the slide blocked the Presumpscot River, flooding upstream areas until nearby mill workers dug the river a new path by hand. A few modern examples include a 1983 spread along the Stroudwater River in Gorham, which you can see here on the Lidar, and this may have been triggered by vibrations from water well drilling for a new home. Everyone at the site escaped injury, but as you can see here, their vans and the drill rig did not. The bottom left photo shows some Presumpscot formation between slide blocks, and the middle photo shows some liquefied Presumpscot formation from test drilling after the event. A nice soupy mess. Now here's something that you probably don't see every day, a garbage landslide. This 1989 event occurred at a large landfill in Norridgewock. Landfills are often sited on Presumpscot Formation due to its low permeability, but some excavation work here triggered a landslide. I apologize for the lack of scale in both photos, but I think there are some excavator tire tracks for context in both cases. So the left photo is a side view that actually shows some very nice spread morphology with slide blocks comprised of garbage. And the right photo shows liquefied Presumpscot formation escaping to the surface. The 2005 rotational slide along the Maryland River in Wells is a classic example of Presumpscot formation failure along a river cut bank during wet spring conditions. No one was injured, but the house in this photo and another nearby home were condemned and torn down. The right photo shows a view of Presumpscot formation in the tow along the river. This site borders the Rachel Carson Preserve, which is over in this area, where another similar but much smaller event occurred in 2019. This is another spring event along a cut bank. The site photos are linked up here with red arrows for some context. Thankfully, no one was on this trail or the observation platform when this happened. And this is another area where the surface materials can be very deceiving. There is a 4 to 5 foot layer of sand over the Presumpscot Formation here, which I hope is apparent in the middle photo. So it's easy for people to forget that it's there. Just a couple more modern examples before we move on. A small 2006 event along the Penobscot River shows some classic rotational morphology. This event did cause some damage to US Route 2, which is right up here, just out of the photo. So that's probably the only reason it made the news. And more recently, a 2020 spread on the Presumpscot River in Westbrook that I will come back to in more detail a bit later. So in all of these cases and more, property was certainly damaged, but no injuries or deaths. So while there have been numerous documented events, the perceived landslide risk has remained low. However, scientists had no idea of Maine's true landslide history until the state began to collect Lidar data in the early 2000s. For example, here is a section of the Swan Pond Brook Valley in Biddeford with the typical pre-Lidar reconnaissance information. Air photos and topographic contours that give the impression of an average forested stream valley. Lidar imagery for the same section shows that the valley is actually full of large spread landslides outlined in red. Hundreds of landslides were hiding in plain sight under thick forest cover. In fact, southern portions of the state had already been mapped at 24K scale by the survey before Lidar, and none of these landslides were included. I want to show just a few more striking Lidar examples. This site in Steep Falls along the Saco River is one of my favorites and a fantastic spread slide example. You can see how the event likely blocked the channel, forcing the river west. The slide blocks shown in this photo on the right were originally mapped as meander scrolls. There's some pretty big meander scrolls. The Stroudwater River Valley just west of Portland is also full of landslides, as you can see here. Slide blocks are pretty obvious in this nicely landscaped yard. The owners had suspected for many years that the area was a landslide after seeing news coverage of the 1983 event that I described earlier, which is just downstream here a ways. But their inquiries were not really investigated, so they were quite delighted when I contacted them many years later with this Lidar imagery. Maine's largest landslide complex occurred along the Saco River in Hollis, where portions of a large glaciomarine delta front failed over time for a total disturbed area of about 741 acres or 300 hectares. Much of this site is public wildlife management area, so it's surprising that the large slide blocks shown here in the right photo went unnoticed for so long. Portions of the slide blocked drainage right here to form Killick Pond, where drowned trees, hopefully you can see them, they don't stick up very far, can still be spotted near the outlet of Killick Pond. Analysis of these trees could help answer a lot of questions about this landslide, as shown in last week's seminar presentation, if you were here for that. This is another large glaciomarine delta failure south of Sebago Lake, which is the water supply for much of the greater Portland area, Maine's largest population center. Much of the landslide is owned by the Water District and open to the public with popular hiking trails. So again, it's very surprising that this landslide went unnoticed. The top photo is a view into the crater from top of the impressive 50-foot headscarp. And the bottom left photo shows where an undulating trail traverses slide blocks. Water mains go through the crater right here. You can see that trace of that line. And I often wonder what might happen if another portion of the delta failed. So over here you have a little bit of erosion and groundwater sapping. So what might happen to this area if something else were to fail? These sites along the Saco River and Saco show more of a flow morphology, which is likely a reflection of the local surficial geology, although the top site is now obscured by a subdivision. The flow morphology seems to be more common in areas with thicker and or more sensitive Presumpscot formation sequences and thin, if any, overlying deposits that simply liquefy, leaving flat and swampy craters with few and or more subtle slide blocks as shown in the right photo. They just become big mosquito factories, I think, from my experience. All right, so I could show LiDAR imagery all day, but I think it's time to move on here to other topics. When I started at the survey, one of my first tasks was to conduct a manual review of Maine's LiDAR and develop an inland landslide inventory. The inventory grew over the years as the state obtained more LiDAR until it was complete in 2020. There are at least 405 inland landslides with a slight majority below the marine limit and an average disturbed area much larger than the typical modern event. This may not seem like a lot in comparison to what other states have, but it is way more than what was originally suspected. The inventory map clearly shows high density of landslides in the most populated area of the state, which also coincides with large Presumpscot formation deposits. But we only knew the ages of 29 modern and historic events below the marine limit. So I set out to determine when and why some of these landslides occurred in southern Maine. The easiest way to determine landslide age in Maine is through radiocarbon dating of organics that were entrained or buried by the landslide. I'm sure you're all familiar with this approach, but I have a side view cartoon illustration here of a slope before and after a landslide to demonstrate this scenario, and I'll use this illustration again in a couple of more slides. The one good thing about Presumpscot formation is that it preserves organics very well. But finding the organics can be a challenge, like looking for a needle in a haystack. A major construction project in Portland uncovered these trees that were entrained in a landslide, and this was the first detailed study of a prehistoric event known as the Brample Landslide by my predecessor, Woody Thompson, and others. This landslide occurred about 13,500 calendar years BP, so it was initially assumed that most of the landslides uncovered by LiDAR also occurred in late glacial times when the landscape was likely unstable. Sampling organics from a landslide buried surface or soil is typically the most efficient approach for working on these landslides, but this is not always possible, especially if the runout was into a river channel. In those cases, I would attempt sampling basal deposits from post-landslide wetlands, but this was much less reliable depending on land use history. Most of the buried soils that I found were remarkable, very well preserved, and probably worthy of a separate study. There are plant fragments, as you can see here in the bottom right photo, that look like they were just deposited yesterday. Seeds, twigs, leaves, just a really interesting snapshot of the local vegetation at that time. The goal was always to sample the youngest material possible from the soil, but sometimes I had no choice but to use wood or charcoal fragments, which are a little bit less precise. So I was able to estimate the ages of 36 sites, and 2 of them likely captured multiple failures. This is certainly not an unbiased sample in any way. Most landslides are on private property, so I could only go where granted permission, and some sites simply did not yield any samples. So this is a summary graph from my study with the most representative sample from each site for sake of simplicity here. The blue bars are surface samples that represent minimum age estimates, while the red bars are buried or entrained samples that represent maximum age estimates. The sites in this study are relatively young. So the one thing that we can say is that the landslides uncovered by Lidar are not all late glacial as originally hypothesized. Into this younger time segment, some clusters of activity become apparent around 600, 3,300, and 4,000 calendar years BP. So it's hard to say what caused these clusters. Unfortunately, I just don't have enough supporting information. This study map shows that some sites within a timing cluster, which are symbolized as such here, some of them are adjacent to each other, but some are not. Earthquakes are an obvious potential trigger, especially in sensitive clay, but we know very little about Maine's paleoseismicity, so a lot more research is needed there. There are also very few modern analog events, mostly just this one, where some small rock slides and falls were triggered by a 2006 magnitude 4.2 earthquake in the Acadia National Park region. Another trigger scenario could be a regional climate event. The 600 BP cluster falls within the medieval climate anomaly to Little Ice Age transition. Limited regional paleoclimate data from sites like Saco Bog and Basin Pond and Sydney Bog indicate that this may have been a dry period with large fires. And some of the buried soils that I encountered from this time period seemed burned with abundant charcoal. So it's interesting to consider the possible effects of widespread fire on hydrology and, in turn, landslides. But again, there's not quite enough detailed data to adequately support any links to landslides. I'd like to circle back to the 2020 Westbrook landslide as a recent example and to show the context provided by Lidar that I have been trying to convey to planning and emergency management agencies. This landslide occurred in late summer of a dry year, which is not typical. Possible factors that contributed to this event include increased overburden weight over time from several sources, such as fill. The area is all fill over Presumpscot Formation. Development, several new buildings had been going in. Aggregate stockpiles. Also possibly exposed riverbanks due to very dry conditions and low river stage, and or vibrations from rock crusher operation in this area. Blocked the Presumpscot River with slide blocks rafted both up and downstream, and a USGS gauge just upstream of the landslide clearly shows the effect of the landslide. Dam closures upstream of the slide helped to prevent serious flooding until the channel could be cleared. This drone photo shows the spread morphology nicely and how failed Presumpscot Formation was quickly being reworked by the river, giving the water a blue-gray hue, which freaked out just about every river biologist in Maine. Site photos show a panorama from the southwest side of the headscarp with some tension cracks. We were worried about this block falling, but it didn't, thankfully. A more direct view into the crater with a glimpse of Presumpscot Formation there. And you can also see an exposed sewer line on the opposite riverbank for some context that'll pop up again in some later photos. Thankfully, the tow did not cause any damage, but it was very close to that pipeline. And then I have some remolded Presumpscot Formation with slickened sides in the tow area. It's likely that the river would have made quick work of the debris, but there were very valid concerns about the integrity of gas and water lines that cross below the channel, along with a sewer outfall just 50 feet downstream of the tow. So excavators were brought in to clear a large amount of the debris. This was not an easy task, as the Presumpscot Formation would simply further liquefy when scooped out of the channel, making a huge mess. I was also pleading caution, as rapid toe removal could have a debuttressing effect, leading to further retrogression, but thankfully that didn't happen. So the sewer line I pointed out in the previous slide, you can see it right here, for some context. So given the context provided by Lidar, a landslide in this area was not all that surprising. There are 17 features along the main channel in this reach, with many more in the surrounding area, all outlined here in red. Zooming into the 2020 landslide area, there are several adjacent features. The 1831 and 1868 events that I mentioned earlier, and a small slump that occurred during gas pipeline installation in 1965. This is not the pipeline area of concern after the 2020 slide, which is located. There are two prehistoric landslides, an area known as the Fuller Slide that is at least 2,200 years old, and another smaller feature for which the age could not be determined, as the crater was mostly full of garbage. This area is all underlain by Presumpscot Formation and is clearly susceptible to landslides. Test borings and a geotechnical study by Devon and Stanford in a large subdivision on the north side of the river found the underlying Presumpscot Formation to be quite sensitive, and calculations based on field tests indicated that this slope should have already failed. This report, evidence indicates that once an initial slump occurs, the subsequent events could be catastrophic and perhaps involve a flow slide of such magnitude as to engulf much of the subdivision as far back as Bridge Street. So as development increases in Maine, especially southern Maine, these types of situations are very concerning. Moving on to the last group of inland-upland landslides, Maine's rugged interior is where most people think landslides should occur, and they do, but are seldom witnessed or seriously problematic due to low population density and limited infrastructure. Maine's highest peak, Katahdin, is littered with slide and avalanche scars, and Lidar imagery revealed an interesting translational slide from the peak of South Turner Mountain, which is just northeast of Katahdin. So here is the literal summit of our Sea to Summit landslide tour. If you've ever been to Maine and hiked Katahdin, you might be familiar with the A-Ball Trail, which was used to go up this periodically active rock slide circled here. Not sure why this slide was originally picked as a trail route, but it cost Baxter State Park $100,000 to move the trail off the slide to a new route that opened in 2016. I have several other modern examples to show, all from the Grafton Newry area in western Maine, where I've been working recently, including a 1927 event on Old Speck Mountain that was triggered by very wet conditions. It's one of the scars in this photo, but we don't know exactly which one, probably one of these ones over here. The local bedrock structure in relation to the glacially carved U-shaped valley undoubtedly makes this a more susceptible area. The 1990 event on Mount Hitty was also triggered by wet conditions and was actually witnessed by a local resident. You can see right here. Ice flow during the last glacial advance was generally northwest to southeast in this area, so deposits on down ice southeast facing slopes tend to be less compact, which may have contributed to this event. Rockfalls are also pretty common on down ice southeast facing glacially plucked cliffs, such as this area here on Bald Mountain. You can see this rockfall here. This is a popular skiing and hiking destination with several vacation home developments, one just a half-mile downslope of this rockfall. You can kind of see it here in this photo as well. So COVID has only spurred more interest in western Maine as an outdoor destination. So while landslides haven't been a problem in the past, they could be with increased traffic and development. Increased storm severity due to climate change could also lead to more events like this 1998 flow in till and glaciolacustran deposits in the Wild River Valley of Gilead, Maine. Lidar has also uncovered many inland upland features, and I must assume that most are prehistoric, as we have not done any formal studies yet. Here are some nice examples also from Western Maine and a couple of different types of materials. I was able to visit both of these locations, but the vegetation was so thick that my photos don't give any sort of impression, which again makes it understandable that they went undetected for so long. The USGS website has several public resources for inland landslides, including case studies, the Maine landslide guide and a story map. The inventory data that I showed earlier can be browsed or downloaded, same as for the coastal data. We do have some susceptibility maps for southern Maine towns, but they were completed pre-LIDAR and so are no longer accurate. For example, Maine's largest landslide complex that I showed earlier is not acknowledged on this map. Updated susceptibility mapping is something that really needs to be done in southern Maine, but in order for it to be useful, the detailed surficial units for all of southern Maine also need to be reviewed and updated with LIDAR, since they are an important input to any susceptibility model. So unfortunately, that would be a major project. To sum things up, Maine has a lot of landslides and we don't know nearly enough about them. There is still so much research to be done, especially concerning Presumpscot Formation characteristics. Due to a lack of serious incidents or sheer luck, the perceived risk is low, which has made funding research and engaging stakeholders more challenging. High property values and new development in susceptible areas will likely increase this challenge. I hope you've enjoyed this tour of Maine landslides from sea to summit, and I'm happy to answer any questions.